Hi everybody. I want to show you a couple of clever questions that show up in this homework assignment. This is a tetrahedron. I got a model of a tetrahedron in the classroom. It's a really beautiful thing. It's a triangular base pyramid, and all the faces, the three lateral faces, are also equilateral triangles. Every edge on this thing is 18 inches. We're going to find the length of the slant height and the altitude, and we're going to study the right triangle made by the slant height, the altitude, and what's called the apothem of the base. And we'll teach you more about that soon. But first, let me draw a slant height. A slant height, you probably know, goes from the vertex to a midpoint of a base edge. It could go to any one of those three base edges, and they would all have the same length. But I'm going to go from V to the midpoint of AB. Call that place M right there. And we know that this is an isosceles triangle, in fact, an equilateral triangle. And that's going to tell us some things about the angles that would be good for us to know. I'm going to find the length of that slant height, VM. I won't have to use the Pythagorean theorem. I'm just going to work out with 30, 60, 90 triangles, although you could use the Pythagorean theorem. I want to know, what is the altitude in an equilateral triangle? Making that sketch. This is like triangle VAB. Right there. Let me back up just a little. I'm going to look at everything. Here's triangle VAB. And each edge is 18. This length would have been 18. And you recognize that this altitude is going to bisect that base in this equilateral triangle, so this length would have been 9 and 9. This is a 60-degree angle, as these triangles are equilateral. And this altitude force is a 30-degree angle there. So we're just about finished with that 30, 60, 90 triangle, aren't you? Hypotenuse 18, short side is 1/2 of the hypotenuse. What about that longer leg? Yeah, short side times the square root of 3. So the altitude there, 9 square roots of 3, which is the slant height here. So that's something that was going to be asked of you. Find the slant height in a tetrahedron, given the base edge. But now I'm going to show the altitude. And here it does get a little bit clever. The altitude would go to the center of the base, and I'm going to call it Vx, as I commonly would. I'm going to call that place X right there. And that Vx, amongst other places, lives in this right triangle right here. And we can work out with that right triangle and figure out the length of Vx. But we're going to need to know the length of Mx first, aren't we? And that's an interesting thought, finding that length. Let me sketch a little equilateral triangle over here, and we're going to work out with it, see if we can't find that. That's called the apothem of the equilateral triangle. This distance is from X to the midpoint. An apothem is used when you find the area of a polygon. It goes from the center of a polygon to the midpoint of an edge, but it's perpendicular. And check out this little triangle we're going to work with right here. I think we know some angles in it, and we'll know a length as well. This equilateral triangle was 18 on the side. This part would have been 9. This full angle is 60 degrees. We could find a couple of congruent triangles right here, but what I know is this is going to be 30. And that would have been 30 adjacent to it, but that's a 30-degree angle and a 90-degree angle, so there we have our beloved 30, 60, 90 triangle with a 60-degree angle right there. So I'm going to work with that triangle. I'm going to find the length of the apothem. We could also find the length of the hypotenuse there, but that's not what's important to me at the moment. I want to know the distance from the center to a side, which is the same as the distance from the center to the side right there. I got a 30, 60, 90 triangle. That side of length 9 is opposite the 60. That must be the longer leg. I want to go to the shorter leg. I should take that number 9, divide it by the square root of 3. That's how you go from the long leg to the short leg. Then I got to rationalize that denominator. I hope you know what this is going to become. When I fix that denominator, I'm going to multiply by the number 1. The square root of 3 over the square root of 3, yielding 9 root 3 over plain old 3. Yeah, we ought to call that 3 times the square root of 3. That's what that length is. That's a good thing to know. That's our length for the apothem here. And if we were caring about the area of this, we might could use that to do that as well. But let me just say that this is 3 root 3 right there. Now, sir, ma'am, if you know the hypotenuse and you know this leg, couldn't you find the length of the altitude? Let's check these interesting numbers out and see what comes. 3 square roots of 3 squared plus Vx squared, whatever that may be, should equal the hypotenuse 9 root 3 squared. Careful treating these interesting numbers. 3 squared to 3 squared, I'm going to square the 3. It will become a 9. I'll square the square root of 3. It becomes a full-on 3. So this becomes 9 times 3. We get 27. Plus Vx squared equals, and you square this one. You get an 81 when you square the 9. When you square the square root of 3, you get a plain old 3. So it's going to be 81 times 3. That's probably 243. Yeah, that's what that is. Let's subtract 27 from both sides. Alexa, what's 243 minus 27?
243 minus 27 is 216.
Oh, 216. That's a beautiful number. That's 6 to the 3rd power. But amongst other things, let's take the the square root of both sides. The square root of Vx squared is just going to be Vx. Now, what do we know about this 216? I think 36 goes into it. I think it's 36 times 6. I know the square root of 36. So it is 6 times the square root of 6. So 36 comes out of the radical, becomes this 6. I do not know the square root of 6 itself. I live it aside. So lo and behold, that altitude is 6 square roots of 6. Now, a beautiful question. Let's find the measure of this angle. Right there. I'm going to call it alpha, just because it's easy to talk about alpha. We're going to find the measure of the angle formed by this face and the base edge, base face. That angle right there. I think we can do it 2 different ways. Probably more than that. Let's work on that together. Show you what we can do. Tell me, could you tell me the sine of alpha? The sine of alpha, well, the sine of alpha would be the opposite over the hypotenuse. That's how you get the sine of any angle. So the sine of alpha would be 6 square roots of 6 over the hypotenuse, 9 square roots of 3. Just for good form, I'm going to rationalize this denominator. We could punch it into a calculator looking like that, but let's just go ahead and rationalize that denominator. Why not? I want to get rid of that radical in the denominator, so I'm going to multiply by the square root of 3 over the square root of 3. And you come along, this is going to give us, in the numerator, 6 square roots of 18. I'll have to work on that in a minute. And here we're going to get 9 square roots of 9. The square root of 9, as I multiply those two, just becomes 3, and we'll have 9 times that 3, we'll have 27. Now let's work some more. We should have worked with this guy, but this is going to be okay. What do you know about the square root of 18? Well, the square root of 18, since that's 9 times 2, I know the square root of 9 is going to come out of that radical, become a 3, multiply with that 6, and that's going to give me 18 square roots of, who got left inside the radical? The 2 did. 18 square roots of 2 over 27. And that amount, my friends, because 9 goes into both of them, is 2 square roots of 2 over 3. Let me just play around for a second. I think it's good for you to see these kinds of things. Let me turn on my calculator. First, I'm going to evaluate this. What is, I'll do it as cleanly as I could, 6 square roots of 6 divided by, and I need parentheses around this, 9 square roots of 3. Yeah, that gives me this decimal amount, huh? But is this the same amount? That's what I really care about right now. Let me try that. 2 square roots of 2, close those parentheses, divided by 3. Oh look, it's exactly the same. My point to you is, it's nice to go through that little job. But we really care about this angle. That was just playing with numbers. Let me go back to what I was working on here. The sine of alpha is 2 square roots of 2 divided by 3. I could use this same number. It gives me the same amount. But what would be the measure of alpha itself? Well, what do you think it would be? I'm going to show this in my classroom and ask everybody what that angle should be. We should arc sine both sides of this equation. The arc sine of the left-hand member just leaves alpha. On the right-hand side, let me say, the angle whose sine, the arc sine of 2 square roots of 2 over 3. Now I got to be kind of careful entering this on my calculator, and I'll take the arc sine of that amount. Actually, because I have that number on my calculator right now, I could go arc sine and then plug in that same amount by going second answer, this part right there, that ANS right above, gives me that same number going to go back in there. So I'm going to take the arc sine of that last number, and it tells me that that angle should be 70.5 degrees. Pretty close. 70.5 degrees. Now, clearly I could do this again. Punch in those numbers, I promise you it would come up with this same amount. So that angle right there is 70.5 degrees. Would that be true in every time you have a tetrahedron? I say, yeah, probably going to be true. Let me show you another question. This is also a little bit involved. Here's the thought. There's some tall thing in the distance, and we'll let it be a flagpole. This guy, Herbert, he sights to the top of that flagpole and he measures this angle, and he sees that it is 10 degrees up from the horizontal to the top of that flagpole. He moves 200 feet closer, whips out his protractor again, measures to the top of that flagpole, then finds it to be 18 degrees. Now we're going to figure out what is the height of that flagpole by knowing those two angles. But it is a little bit involved, and I'll tell you, next week I'll show you a better way of doing it that's quicker. But let me show you this way first. We're going to have to figure the height of this flagpole. I'm going to have to do something about this length. I'm just going to call it X for now. I'm going to have to include this as I work in this direction. What do you know about this angle, 10-degree angle, and you wish you knew its opposite, and you got this idea about it's adjacent. And if I were going to use opposite and adjacent, I could use the tangent function. Put a little SOHCAHTOA on here if that's helpful. Because I'm working with the opposite and the adjacent leg, I do not even care about the hypotenuse, do I? I'm going to use the tangent function. I'm going to have to use it a couple of times. Watch this. What would you say for the tangent of 10 degrees? According to this picture. Well, the tangent's opposite over adjacent. Opposite of this angle is F. And the adjacent is 200 plus X. Okay, let's move a little closer. Measure it again. And because we're looking at opposite and adjacent, we're still going to talk about the tangent, but this time it's the tangent of 18 degrees. I asked you, according to the diagram, what is the tangent of 18 degrees? Write it right here. Tangent of 18 given by the opposite over the adjacent would be F over X. Now, we've got to work with these for a moment. We could put a decimal in for these couple of numbers, and that's probably what we're going to have to do. Okay, that's what I'll do. Let's look up the tangent of 10 and the tangent of 18, and I'll replace these values here. I'm going to do that so you won't have to watch. I have replaced the tangent of 10 degrees with its value. I got it from my calculator. The tangent of 10 is approximately 0.1763. So I just wrote this equation again with a proper valuation for the tangent of 10. Over here, same idea. The tangent of 18, according to my calculator, still got it showing, I think. Tangent of 18 is 32.49. So now, I can cross multiply here, couldn't I? That's what I'll do. And let's get a couple of those things going pretty quickly. Let's put this over 1. And I'll have F times 1. I'll have F here is equal to, and let me multiply these. You do this with the calculator as well, 0.1763. Clear this, 0.1763 times 200 gives me 35.26 as I multiply this times this. 0.1763 times 200 gives me 35.26 plus 0.1763 times x, 0.1763x. Okay, I'm going to hold that thought. Let's see what we can do with this as well. I can cross multiply, and I'll get f, the product of the means, f equals 0.3249x. Okay, well, what can I do now? Done. Have not quite exhausted myself. I look at these and I realize that they are both equal to f. Therefore, these things must equal each other. But a big percentage of this geometry class is realizing that's true and finding out when you want to equate two things, figure out that they equal the same thing, therefore they equal each other. Let's set these equal to each other. We're going to have to find x first. So 35.26 plus 0.1763x must equal f, which in turn equals 0.3249x. 249x. We're going to solve this for x. I guess I ought to subtract 0.1763x from both sides. Take it away from this guy, huh? I'll do that with a calculator. 0.3249 minus 0.1763 gives me 0.1486. 0.1486x equals, what's left over here is 35.26. Now, can we solve this for x? I figured we could. I'll divide both sides by 0.1486. This is a little bit involved. And I'll tell you, you're going to love it when next week I show you the quick, clean way of doing this. But we're going to get it this way first. I'm going to get the value of x. These divide cleanly to leave just x. So I got to get this quotient. So I could say 35.26, you do it too, divided by my last answer. So I'm thinking it's 237.3, pretty tall, huh? 237.3 feet tall. Whoa. Heck of a flagpole. That's not the flagpole. That's the ground length, isn't it? 237.3, excuse me. 237.3 feet. Now, can you get the flagpole, mister? That was the value for x. And yeah, I could. It won't be bad at all. I can just use this right triangle. I'll stick with that tangent function, though. I think, what would be the tangent of 18? Now that I know this adjacent leg, I'll work it in this little corner. I'll find a place to work that question. Gotta find the height of that flagpole, and what could we know for sure? What do you tell me about the tangent of 18? Why'd you decide to use tangent, mister? Well, I'm not concerned with the hypotenuse, so I don't care about sine or cosine, which both involve the hypotenuse, but the tangent has opposite over adjacent, which works beautifully here. The tangent of 18 is f over adjacent, opposite over adjacent, therefore 237.3. But what else is the tangent of 18 equal to? Let's put it right there. Continuing this statement, the tangent 18 is 0.3249 over 1. Seems like I can get x out of that, f out of that, can I? I can get the length of that flagpole. So I got to cross multiply though, and 1 times f is going to be the height of that flagpole is equal to 0.3249 times 237.3. You're doing it too, I hope. 237.3. I'm thinking, oh, that's better. How about 77.1 feet tall? I got 77.09. That's pretty close to 77.1 feet tall, and that's a respectable height for a flagpole. That's a nice little thing for you to do. There are a couple of other interesting questions. You talk to me about them, and we'll be figuring them out too. Happy to see you. I got a nice assignment coming with this. Thank you, everybody.